All right, welcome back, everybody. So we just finished up with Chapter 5. We were talking about minimization principles and discrete Fourier transforms. And now we are at the final stretch here, or final stretch, what would you call it? Yeah, the home stretch, there we go. Or the home stretch for the semester. And what we are going to do with the rest of the semester is get through our material in Chapter 8, which is talking about eigenvectors and eigenvalues. And if there is time, maybe we'll have a little bit to say about iterative schemes and give you a bit of an introduction to what we use those for. But if we are going to start with the Chapter 8 material, we need to recall a few things from first semester linear algebra. But in your textbook, they give a bit of an introduction or motivation based on dynamical systems theory. Specifically, they like looking at first order systems of equations that you would see, say, in a semester in a class on ordinary differential equations, or the first class in ordinary differential equations. But we are going to skip that for our purposes because our applications are a little bit different. And I'll tip my hand a little bit here as far as your project goes, your final project. This theorem, if you feel like screenshotting or just going straight to the page in the notes, this is going to be your workhorse for the final project, right? So we are going to try our best to build up this theory so that you have enough time to work through your project and get some meaningful results. So we'll talk about the final project in class a little bit, or maybe a little bit later or sooner, just not right now. We will talk about it though. So feel free to start looking ahead to using this theorem, the low rank approximation theorem, because this is going to be how we, or an elementary compression algorithm, very much like we were looking at our discrete Fourier transform as a way, we would filter out the discrete Fourier transform and effectively have a low pass or a high pass filter for some signal. This is going to be that version, that theorem that you're going to be using for a compression algorithm, or at least an elementary compression algorithm. We can discuss more in class, but for now, let's work up to it. So we are trying to figure out how to get to that point, and we need to know, we need to remember some facts from linear algebra, our first semester. So this video is just going to be a quick review of what you need to know from about eigenvalues and eigenvectors, just reminding you how they work and what they do, and how to compute them. Right, and in the next video, we'll maybe do something a little bit new. Right, we'll try to recall certain facts that you'll need to know, and then show you something new that's gonna fall into the realm of practical linear algebra, and how we throw these guys into the computer and what happens. So, quick review. We're going to remember we're going to remind ourselves how or what the objects are in play here. So let's go ahead and define or take a square matrix, so an n by n matrix, and f is just going to be some arbitrary field. We're going to take a scalar lambda in f and call it an eigenvalue if there is a non-zero vector sitting in fn such that a times v is the same thing as lambda times v. So in other words, matrix multiplication looks like scalar multiplication along this vector. Such a vector is going to be called an eigenvector of A associated with lambda. All right, and this should be a very familiar definition, but maybe a little bit different, right? Something a little bit out of the ordinary. We're going to go ahead and let L be a linear operator. So what you can think of here is V is just some arbitrary vector space over a field F. And L is it's just a linear transformation, right? So this is the general object. So L is, just to be very clear, L does not need to be a matrix, right? L could be something like we're differentiating a function, or we're integrating a function, right? So this is going to give you some linear function on this vector space. So from the vector space to itself. Now, scalar in this case is going to be called an eigenvalue of L if there exists a non-zero vector such that L applied to V is equal to lambda times V. Such a vector will be called an eigenvector of L associated with lambda, and if V is a function space, we will use the term eigenfunction in place of eigenvector. So again, this is kind of the new context. And we're going to see this maybe a little bit here, but it's just to hammer home the point that this is a general construction, and it does not necessarily just restrict itself to matrices and just Euclidean spaces, Euclidean vector spaces. So the familiar examples. If we were to think of this matrix, this nice symmetric A matrix, we can find that this guy has eigenvalues of 5 and 3, right? And we can do that very, very quickly. This would be the determinant of 4 minus lambda, 1, 1, 4 minus lambda that we're setting to 0. So we get 4 minus lambda squared minus 1. And this will be lambda squared minus 8 lambda plus a 15, and that guy factors nicely. Lambda minus 3, lambda minus 5. And that's exactly where we pick up these two values, right? Nothing to it, okay? So from there, we compute eigenvectors. And those eigenvectors are found as the null space, or the kernel, of A minus lambda I, right? And just to put it down, this is the kernel of A minus lambda I. And if we were to do this just say for lambda 1, lambda 1 equal to 5, then we wind up with, let's see, A minus 5I is going to be minus 1, 1, 1 minus 1. And we solve that guy against the 0 vector, and we wind up with what it'll be exactly the span of that. So the kernel will be the span of that vector. And V1 here is going to be what we call an eigenvector for that matrix A with eigenvalue or associated with the eigenvalue lambda equals 5. Right? Very similarly, we could pick up V2. And we can verify that these guys are indeed eigenvalues and eigenvectors just by carrying out the computation. What is A times V1? Well, multiply this guy out and then factor out what you think is the eigenvalue. And you should get back the vector that you fed in, or at least a multiple thereof. Okay, so that should be familiar. What's new now, let's think about a linear operator here, going from smooth functions to smooth functions, right? That's a vector space. And we're just going to say that L is the derivative operator. So I would like to find all functions f and eigenvalues lambda, or all scalars lambda, such that lambda of f is equal to, or L of f is equal to lambda times f. So L of f is just simply going to be the derivative, and we need the derivative to be equal to lambda times the original function. No differential equations are not a prereq for the class, but it's useful to us to recall that this is a fact from Calc 1, maybe even Calc 2, but that the functions that satisfy that equation are exactly multiples of e to the lambda x. And this guy represents a basis for the eigenspace. Or this would be the collection of all lambdas, right? Turns out for any lambda, we wind up with an eigenfunction in this case. Even for the case where lambda equals 0, the eigenfunction would be a constant. Okay. Another example, second derivative operator. The eigenfunctions in this case, right, we're looking for f double prime equal to lambda times f, and we wind up with 3 cases. Again, this is from differential equations theory. No, it's not a prerequisite for the class, but it's making an example of what sorts of functions or what sorts of objects we can have in general. So you can verify the second derivatives of any of these guys in the table or in this bracket are going to satisfy this second derivative equation. Or, yeah, f double prime is equal to lambda times f. as a remark, we are working with an eye toward computational algorithms, so it's not too often that we see this this case where we have a plain old linear operator instead of just a matrix that we're trying to find the eigenvalues of. So this with our work toward with our eye toward computational algorithms and doing work in computers, we usually have to go toward finite dimensional problems. So either we're already dealing with something sitting in Rn, or we have some n-dimensional vector space, which I'll remember to put back in red ink. We're dealing with some n-dimensional vector space, and all n-dimensional vector spaces are isomorphic to R, or Rn, excuse me. Now this is something that I have in the notes if you feel like it. This is the chapter 7 material, right? So if you feel up to it, there's a fair bit of stuff that we actually glossed over. Don't have to worry about it because we are not testing on it, okay? But the idea is that we can safely only study linear operators on Rn, so just our usual matrices, or our linear operators on Rn have representations that are matrices, that are nice square matrices. So technically, for our purposes, we really do only need to study matrices. The theory does get a little more subtle for infinite dimensional vector spaces or infinite dimensional operators, but there's a lot of really interesting theory that comes out of making that assumption that you're not in a finite dimensional space. So feel free during class to ask me about spectral theory if you're curious about what happens in this setting. Otherwise, we remind ourselves that the equation that we're dealing with when we're computing eigenvalues for some square matrix, and we're going to do this for real entries, is going to be finding the complex numbers, not necessarily real numbers, that satisfy this equation where the determinant of a minus lambda I is equal to 0. Why is this the equation that we care about? A lot of the time, students just completely skip over asking why we're looking at this equation, right? This is going to be a polynomial in lambda, but we often forget why we're even using this a minus lambda I matrix in the first place. So let me remind you, in our definition of eigenvalues and eigenvectors, we have AV necessarily being equal to lambda times V. Now, lambda times V, I can just as easily write by factoring or by putting in an extra factor of an identity matrix on the right side. Now, why would I do that? Because otherwise, when I try to carry out the algebra here and say AV minus lambda V is equal to the 0 vector, I would like to be able to factor out the V from the right side, but I can't do that because A minus lambda is not a well-defined object. A is a matrix, and I'm subtracting off a scalar? No, I need to make sure that I take the difference between two matrices. And that's exactly why I have to pull out that extra factor of the identity, right? That'll get me a matrix, so this difference is well-defined. Okay, so what happens when I do that? Well, we notice instantly that there's always the trivial solution, right? This guy is a homogeneous equation. It's some matrix times V is equal to 0. And the fact is, linear equations, homogeneous equations, linear homogeneous equations always have the trivial solution as a solution. So what we're really looking for are the non-trivial solutions. And these come from a non-trivial kernel. All right, so this is exactly why we need to make sure our eigenvectors are non-trivial, because we're looking for the interesting solutions to this homogeneous equation. So we will always wind up with a non-trivial kernel if the columns of A minus lambda I are linearly dependent. So this occurs if and only if the inverse of A minus lambda I doesn't exist. And the final step here in the line of argument is that this inverse doesn't exist if and only if the determinant of A minus lambda I is equal to 0. And this brings us full circle to tell us that we're using this characteristic polynomial equation, or characteristic equation for short, in the correct way. So, as a definition, we should remember for square matrices, the polynomial, and it is a polynomial, right? This is the determinant of a minus lambda I. The polynomial that we get in lambda is called the characteristic polynomial of a, and the equation that is the determinant, or setting the characteristic polynomial equal to 0, is called the characteristic equation of a. Now, another familiar example then, we're using the same guy, right? We actually did this computation on the previous page. Go figure. So we've already done this guy. So we know that the eigenvalues are either 5 or 3. If I carry out the computation a little bit further to get the eigenspaces, or the null space associated with lambda equals 5 and lambda equals 3, then this is how I would go about doing it, or this is the way that I like to do it. I set up my matrix and put it into row echelon form as best as I can. And I notice if I have a 0 row after row echelon form, I'm doing things right. I always need at least one row of zeros if I'm going to get a non-trivial kernel. So if you get to this point and you fully row reduce your matrix and it doesn't have a row of all zeros, you have done something wrong. It can have more than one row of zeros, but you need at least one to get that non-trivial kernel, right? So if you don't get that, that means that your selection, your candidate for the eigenvalue is wrong. But once I'm here, remember that matrices or augmented matrices correspond to systems of equations. So I'm just going to go ahead and say that V vector is equal to components V1 and V2. And then this matrix, this augmented matrix produces the following system of equations in V1 and V2, which I can then go ahead and solve for V2 in the first equation, and note that, or solve for V1 in the first equation so that V2 is free. And then I go ahead and say, okay, since my V vector, my arbitrary V vector is V1 by V2, I just go ahead and replace the V1 with a V2 as per my solution to the augmented matrix system. And this gives me some multiple of the vector 1, 1. All right, and this is exactly what we found on the previous page. This vector in the red box is what I'm going to call this is like the eigenvector, but there really is an infinite number of eigenvectors. Why? Because this is a kernel, and kernels are vector spaces. In particular, non-trivial vector spaces have infinitely many vectors in them. So it's really the dimension that we care about, and we get a basis for that kernel. And I'm just going to go ahead and choose this vector to represent that basis, or to represent that entire vector space. Now, the eigenvector basis is for this space, which we're going to go ahead and call V sub 5, and generally this is V sub lambda, where we're going to go ahead and keep substituting lambda with some eigenvalue for the matrix A. But regardless, we have an eigenvector basis for what we're going to go ahead and call the 5 eigenspace, or the eigenspace for lambda equals 5. Very similarly, if lambda is equal to 3, we can go ahead and produce the other eigenvector that we had on the previous page. And this constitutes an eigenvector basis for the space V sub 3, which is the eigenspace corresponding to lambda equals 3. And we now have an eigenvector decomposition of R2. So let's take this one step further. So things that we should remember here. Notice that this matrix A, this particular one, new example, it's a diagonal matrix, and it just has one eigenvalue, right? And the characteristic polynomial for this guy is just going to be 2 minus lambda times 2 minus lambda, so 2 minus lambda squared. Now, for the linear factor 2 minus lambda, there is a power associated with it. And that power is what we're going to go ahead and call the algebraic multiplicity of the eigenvalue. So it turns out that lambda equals 2 here has an algebraic multiplicity of 2. So if we were to compute the eigenspace, I don't know why I switched to e's. Maybe I could just go ahead and fix this right here. V sub lambda, no, we're going to call that e sub 3. And this guy will be e sub 5. And then this guy up here will be e sub lambda. Eigenspace sub lambda. There we go. That may have been for notation in the book, to match the notation in the book. But anyway, so the eigenspace corresponding to lambda equals 2 for this matrix, actually you can go ahead and compute, right? So A minus 2i in this case is just going to be the 0 matrix, which means that its kernel is all of R2. So you can just go ahead and choose whatever basis of R2 you want. And I just chose the standard basis because why not? Right? So the dimension then of the eigenspace is 2, and it equals the algebraic multiplicity of lambda equals 2. Let's go ahead and look at a similar matrix. We'll call this guy B. And B is going to be an upper triangular matrix, but he's still going to have 2's on the diagonal. And we're going to go ahead and kind of put a 1 in this top right corner just to screw things up a little bit. Same idea, lambda equals 2 is still the only eigenvalue. And in fact, I wind up with exactly the same characteristic polynomial between A and B. Right? These guys have the same characteristic polynomials. So they have the same eigenvalues, right? And we know this because you can, on a triangular matrix, you can just read off the eigenvalues off of the diagonal. That's upper or lower triangular. But what's interesting in this case is that B minus 2i is not the 0 matrix. In fact, it's equal to something with a bit of a problem for our row echelon form. This guy has just a one-dimensional eigenspace. So that means that we have an eigenvalue with a basis that whose dimension, or with an eigenspace whose dimension is less than what the algebraic multiplicity from the characteristic polynomial says it should be. This number, right, the dimension of the eigenspace is what we're going to call the geometric multiplicity, right? And this is actually what we see in the vector space as the directions, or the vector spaces that can be scaled as if with multiplication by the matrix, as if it was just a scalar multiplication. So being able to distinguish between these two cases, right, if we're talking about eigenvalues and eigenvectors, it means that we're going toward diagonalization. And diagonalization here, A is already diagonal, but B is close to, but not diagonalizable. We can't make it diagonal. And this is because of this fact that the geometric multiplicity does not match the algebraic multiplicity. So we make a definition to distinguish when we can do this. An eigenvalue lambda of A is said to be complete if its algebraic and geometric multiplicities are the same. And the matrix A itself is complete if all of its eigenvalues are complete. Right? It might be worth checking out a few examples either on your own or in the book, in the exercises, to see when this happens, and especially for higher dimensional systems, like what can happen, how much degeneracy do you get between the geometric and the algebraic multiplicities. Remember that you can have a deficit of more than 1 in this case, but the dimension of the eigenspace is always at least 1, because you need to have at least 1 eigenvector per eigenvalue. But we don't necessarily have to have a complete set. We don't have to fill up what's required from the characteristic polynomial. So in the next video, we're done with our quick review of eigenvalues and eigenvectors and what goes right and what can go wrong. The next video is the different properties that we want to remember about what these vectors can do, and how they interact with each other, how we can make bases. And we're going to learn something new along the way, which is, again, something to do with what happens, or a consideration we need to make when we throw this problem into a computer.